Hello everyone, I'm Kenji Tojo from ETH Zurich. In this video, I will introduce a work on simplifying Radiance fields into an efficient triangle superrepresentation, enabling seamless deployment on mobile devices. Radiance field reconstruction techniques take multi-view images as input and reconstruct a 3D scene as a spatially varying and view-dependent color distribution called a Radiance field. The output Radiance field enables high-fidelity overview synthesis, enabling applications such as interactive scene exploration. A widely adopted Radiance field representation is 3D Gaussian splatting, where scenes are represented as collections of explicit 3D Gaussian primitives, which are rendered through back-to-front composition of the translucent primitives. This representation enables high-fidelity view synthesis while supporting real-time rendering. However, Gaussian splatting typically requires millions of primitives to represent sharp structures and high-frequency details. Moreover, rendering of Gaussian splats relies on costly depth sorting to correctly alpha blend a large number of translucent primitives. These issues make it difficult to efficiently deploy the reconstructed Radiance fields on resource-constrained devices such as laptops and smartphones. To address these challenges, we aim to simplify Radiance fields into a drastically reduced number of triangle primitives that are rendered using standard rasterization through the depth test. Specifically, we represent a scene using only 10 to 20,000 triangles, where detailed appearance is encoded in textures that store color features and binary opacity. This representation enables straightforward real-time rendering and efficient transmission on mobile devices. However, unlike translucent rendering, the depth-tested rasterization is fundamentally non-differentiable. It means that only the visible surface receives gradients, while occluded triangles remain unoptimized. The question is, can we robustly optimize opaque triangle representations while fully relying on the standard rasterization framework? To address this challenge, we draw inspiration from recent implicit surface reconstruction techniques and model rasterization as a discrete stochastic process. Specifically, we assign an existence probability to each primitive and introduce stochastic masking procedure into the rasterization pipeline. In stochastic masking, primitives whose probabilities fall below random thresholds are discarded, while the remaining primitives are rasterized normally. Since the rasterization is now stochastic, visibility also becomes probabilistic. The probability of a triangle becoming visible can be derived directly from the probabilities of the primitives in front of it. This way, the pixel color becomes a random variable, and the loss function, like a standard L1 loss, becomes an expected value over the stochastic rasterization process. This expected objective function can be differentiated using a likelihood ratio estimator by treating the rasterizer as a sampler. Specifically, the expected gradient decomposes into a color gradient term and a log probability gradient term. Thanks to the logarithm, the probability gradients can be evaluated independently per primitive, enabling sort-free optimization of probability values. During training, the probability values naturally converge towards 0 or 1, producing binary visibility masks used at inference time. To represent texture, we leverage the mesh color approach, which does not require a predefined texture atlas. During training, we additionally employ multi-resolution parameterization to stabilize high-frequency texture optimization. Finally, let's take a look at some results. In this example, we evaluate our method in the extremely low primitive setting, using only 15,000 primitives. Standard 3D Gaussian splatting struggles in this low primitive regime and produces blurry renderings. TextureJS improves fine details by introducing textures into Gaussian splatting, but several regions still remain blurry. In contrast, our method preserves significantly sharper structures and achieves the highest visual fidelity under the same primitive budget. Also, our triangle superrepresentation enables seamless real-time rendering on mobile devices, where we can simultaneously load all 14 scenes from the Nerf synthetic and Shelly datasets. Our runtime rendering fully leverages the hardware rasterization pipelines and is significantly faster than the rendering of Gaussian splatting variants. For further details, please refer to our paper. Thank you for your attention.